Good morning. I am Dr. István Szintai. Let me show you the world in my eyes. Before I fulfill my promise to slow down the rotation, let's put the sphere to an orbit around the star. If we do so, then the sphere would be irradiated not from infinite distance, but from finite distance. And as the stars are usually bigger than the objects orbiting around them, as an example, the Sun is 100 times bigger in diameter than Earth. Because of this, more than the half of the surface of a sphere would be irradiated from a star because of the geometry. I will get back to this topic later. Before slowing down the rotation, let's put the fast rotating model to a circular orbit around the star with the axis of rotation parallel to the plane of the orbit. In this case, there will be two positions per orbit where the standard temperature model will be valid when the subsolar point is over a pole, and there will be two occasions when the fast rotating model will be valid and the star is over the equator. So the subsolar temperature will not be constant, but we will have two maximums and two minimums per orbit. It exists a physical property that changes cyclical meanwhile one orbit, and this is the ground speed of the subsolar point, which changes between 0 and 1, only the unity is unusual. This speed will be proportional to the road that the subsolar point takes over one rotation period, and this one will be proportional with the cosine function of the incident angle of the Sun, which we can see from the equator. This is called declination in astrometry. So the dimensionless number that we have to write in the performance balance equation is not going to be constant, but it will change along the orbit. And the addition, what is above 1, is going to be proportional with the cosine function of the declination. So the relation between the incoming performance that keeping balance with the temperature would look like this. Now we can make the slow rotational model. Let's imagine a sphere that not rotates regard to outer view, and let's put this sphere to a circular orbit around the star. In this case, the subsolar point will move along the equator with a constant speed. This is the same situation if the rotational axis is perpendicular to the plane of the orbit. In this case, if the rotation period and the orbital period is the same, then the subsolar point will be at the same point on the surface of the sphere, so the standard temperature model will be valid. In this case, rotational index would be 1. And if the rotation is faster, then the maximum of this value is going to be pi, as we saw in the third episode. So rotational index is going to be a property of a planet. Let's put the sphere to an elliptical orbit around the star. In this case, the available performance will change, as we saw in the second episode. So I added the square of the distance between the star and the body. And if, as we know, that the speed of the orbit, the orbital speed of the object, is not constant, so if we think that the sphere not rotates regard to outer view, then the speed of the subsolar point, the ground speed of the subsolar point, is not going to be constant, but it will be high at perigee and low at apogee. So the rotational parameter we have to modify depending on which place we are on the orbit. But this rule, I don't know, and I cannot figure this out. So I will use an f function to mark this unknown thing. Only we can know that the rotation index modified with this f function is also must be between 1 and pi. There is only one situation left when the sphere is on elliptical orbit around the star and the rotational axis is neither parallel nor perpendicular to the plane of the orbit. This is the situation where we live. We can put together the findings we did before. So the performance balance equation between a sphere and a star would look like this in general form. It's very interesting, so I make a little summarization. We know the sigma, the Stefan-Boltzmann constant. We know the distance between Sun and Earth. We know the declination of the Sun at every day. We don't know how much irradiation we should write in that equation because everybody else say that we cannot enter the incoming performance, the sum, simply. We don't know how much is the rotational index regard to Earth, but we can make a bluff. I don't know what would f function look like, so I will use 1, as it would not exist. We don't know the surface temperature of the Earth because we do not measure and we do not record the surface temperature. We measure and record the temperatures of the air, of the atmosphere, but we don't know the daily average temperature of the subsolar point. This is missing for public. But we have meteorological stations that can be subsolar points. So I will use this to make a quick look. This is going to be the most rough approximation. I choose 3 meteorological stations, one on the Tropic of Capricorn, one from the Tropic of Cancer, and one from the equator. Because of the geography of our planet, these places usually highly elevated. This is going to be the most rough approximation. I will use 3 months of daily maximum values from Tamara set and from Gobabis. And I will use 2 months from Kishumu, which is on the equator. We can make a plot from a year. So on the x-axis is the day of the year. And on y-axis is the temperature in Celsius. We can write up that function we discovered. At first, we can see that when the sun is over the equator, we counted the values we measured. But in July and in December and the surrounding months, the situation is not good. We have the double maximum curve. We have the values of the maximums. We have the values of the minimums. But the positions of the maximums is not correct. Could it be that the unknown f function is the cause of the difference? To figure this out, I used a mathematical trick. I mirrored the actual total solar irradiance to the average total solar irradiance. And if we think that orange graph is close enough to the measurements, then we can write up an equation whether the unknown f function is the reason or not. As you can see, this is not going to be good because there is some situations when the rotational index multiplied with the f function is going to be higher than pi. So f function alone is not enough to produce these numbers. So, Houston, we have a problem. In July, there is not enough incoming performance from the sun to cover the temperature radiation of the subsolar point on Earth. What this means? Earth and atmosphere system seems not to be in immediate performance balance with the radiation of the sun. Seems that between April and September, the heat radiation of the atmosphere is higher than the electromagnetic performance income from the sun. And controversy, from October till March, the heat radiation of the atmosphere is lower than the electromagnetic performance income from the sun. Seems that this performance imbalance can be a function, although I don't know it yet. But one fundamental logical step is still missing, because all literatures say that the available total solar irradiance we should not write simply in the performance balance equation. And of course, where is the performance of the reflected light? I did not mention yet, but the heat radiation of Earth at that temperatures we measure and where we live is not contains shortwave radiations. What we have to do? We have to clarify whether it is hotter or colder close to the sun compared when Earth is far from the sun. We have to count the daily average of the subsolar air temperature to make a goal to count with the functions. And if anybody starts that counting, then please count the daily average temperature of the day side of Earth. At first, the mathematical 90-degree would be enough for Terminator. So we can raise a lot of questions, especially what is the correct value of the rotational index of Earth and how that unknown f function looks like, and where is the performance of the reflected light. So to figure out these questions, I will need a simpler example than Earth, because on Earth there is atmosphere, and atmosphere has a mass and a heat capacity, and atmosphere can transfer heat in horizontal way, and on Earth it exists water, and water has a mass and heat capacity also, and water can transfer heat in horizontal way and in vertical way as well. So I will need a more simpler example. So in the next episode, we will start our trip to Moon. Be well, and don't forget, the sun will rise tomorrow morning for sure.